Okay, in this video, we are going to continue to work on some more advanced FOL translations. We're going to start with a puzzle and then introduce some of the concepts we will need in order to solve that puzzle. The puzzle is a puzzle for something called the law of excluded middle, which says that for every proposition, either this proposition is true or its negation is true. So P or not P for every proposition, either P or not P. For example, it's either raining or it's not raining. What should we say about a proposition like this one? The present king of the United States is bald. Is this proposition true or false? Obviously false, right? But what about the negation of this proposition? What if we add the present king of the United States is not bald? Now what's the truth value of the proposition? Still false, right? So this looks like a case where the proposition and the negation of that proposition are both false, which seems like a problem for the law of excluded middle. Now, you might be thinking, but the present king of the United States doesn't exist. Surely that's part of the issue here. And you would be right. But the question is, what should we say about the law of excluded middle? Here are a few options. Reject it. Maybe it's not a general principle and it doesn't apply when a part of the proposition refers to something that doesn't exist or something like that. Or maybe a statement like the present king of the United States is meaningless when the name doesn't refer to anything, then the entire sentence in which that name occurs is meaningless. The problem with that is it doesn't seem like a meaningless sentence. We understand exactly what it means, and we understand that it's false, and we understand why. So, like, in what sense is it meaningless? So our third option is that maybe the grammar of the English sentence is misleading. And let's explore that one before we reject the law of excluded middle. And we've already seen other English sentences where we've had to come up with sort of ingenious ways of expressing them in a precise way. For example, the grammar of this sentence is such that everyone is the subject, it's the grammatical subject, and is bald is the grammatical predicate here. But the grammar of this sentence makes it seem like there is some individual, everyone, that has the property of being bald, such that we should translate it like this. But that's not what the sentence means. It doesn't mean there's some one individual that has the property of being bald. Instead, we've come up with a way to capture this using quantifiers. We will write, there is this domain with objects. We must specify what it is. Let us say that it is people. What I'm saying here when I say everyone is bald is that for every single thing in this domain, that thing has the property of being bald. And likewise with the one down here. This is the grammatical subject, this is the grammatical predicate, but we aren't predicating baldness of some particular individual. At least in this case, it is one individual and not a whole group of individuals if the domain includes more than one person. But it's not a specific individual. So we have been translating this using a quantifier. There is an X, some X in the domain. I'm not saying which one, just there is one, such that if you put it in the blank for the predicate, it will be true. At least one object in the domain will fit in that predicate and it will be true. So what we're going to say here is that this is a predicate, but just like everyone and someone are not names of a specific existing individual, the present king of France isn't a name that picks out or refers to an individual. We're going to say this is not a name. Well, then what is it? It's a definite description. Okay, well, what's that? We'll get to that by the end of this video, and when we do, we will translate this sentence into our symbolic notation and then show that it doesn't violate the law of excluded middle. And maybe you noticed that I switched from the United States to France. In the original example by Bertrand Russell, this was the sentence used: the present king of France is bald. And we'll use that from here on out. Okay, so before we get into definite descriptions, we need to review and introduce a couple of concepts. So the first thing we need to review is multiple quantifiers with overlapping scope. We introduced this previously. Let's let our domain be people. And let's use the good old loves predicate. So LXY is X loves Y, and let's let M be Mary. Okay. Mary loves, actually, let's do it the other way around. Let's do someone loves Mary. How should we translate this? Well, this one does not require multiple quantifiers, much less multiple with overlapping scope, but there exists an X such that X loves Mary. What about someone loves everyone? There exists an X such that for all Y, X loves Y. So there's at least one person in the domain that loves every other single person in the domain. This is the at least one, and then every other person in the domain could be slotted into the Y spot here to make a true sentence. But this also includes X loving themselves, right? So someone loves everyone, including themselves. Why? Because X and Y can be the same individual. Nothing guarantees that this X and Y, that the value that this X and Y can take will be different individuals, or names of different individuals, rather. So what this says is someone in the domain, at least one person, loves everything in the domain. And whatever satisfied X here is a thing in the domain, so X will end up loving itself. What if we wanted to say someone loves everyone except themselves? How could we express that? Well, there's still someone, and we're still talking about everyone. There exists an X such that for everyone in the domain, if, I'm going to introduce a new predicate here, if it's not the case that Y is identical to X, then X loves Y. So that says someone loves everyone. What do you mean identical? Like twins are identical, right? They look identical. I don't mean they share some things in common, genes or physical features of some kind. I mean, they're literally the same thing. They're numerically identical, is the jargon here. So let's let this predicate, a two-place relation, mean, so defining it as a predicate here. This predicate means X is literally numerically identical to Y, which is to say X is the same individual as Y. Now we could just add this to our key up here, I, X, Y, and then fill in everything I just put in blue. But this predicate is so useful, we can use it to express so many things, that we're going to add this predicate with this intended interpretation to our language. You don't need to put it in a key. We'll always just know when you say identity, this is what it means. And additionally, because we are more familiar with this symbol for talking about identity, we're going to do it like this instead. We'll just put this down here. This is what I mean. Forget the usual, this doesn't look like any of our other predicates. We usually use what is called prefix notation for our predicates. This doesn't really fit the grammar of our language, but because it's more common and it looks familiar, we're going to do it this way. And likewise for not equal. Instead of doing this, we're going to do this. Unless that symbol is a pain in the butt to find or look up, then feel free to do this. Doesn't really matter. It's just that these are familiar, people know what they mean, so we're going to just do it that way. Okay, so we've introduced the identity predicate. We're just adding this to the language, and it means is the same individual as. So what are we going to do with this identity predicate? I said it's really useful. Well, let's talk about quantities of stuff. We have our existential quantifier, so we can write something like EX, PX, and we said the existential quantifier means at least one. If our predicate P means, I don't know, something boring like we've been using, is mortal, then this means at least one, assuming the domain is persons, people, at least one person is mortal. Someone is mortal. That's kind of a weird thing to say in natural language. If you ask for some of the fries and someone gives you one, that's not what you meant. But what this is precise, and our logical language is precise. At least one is precise. Here are some other things we can say numerically and be precise. We can say it is not the case that there exists an X such that PX. That means no one is mortal. How many mortal people are there? 0. So we can express at least one, and we can express 0, and we can express all. We don't know exactly how many that is, but all, everything. We might want to express some stuff in between. And that's what the identity predicate is going to allow us to do. So I'm going to erase all this. So let's say that I wanted to express there are at least 2 things. Not at least one. There exists an X, predicate X, that means at least one. But what about at least 2? there are at least 2 cats, let's say. How can we express this? There exists an X and there exists a Y such that X is a cat and Y is a cat, and there's more. This isn't enough. So far, we haven't guaranteed that there are at least 2 because, as we've already said, X and Y could refer to the same object or be satisfied by the same object. So this would be true if there was only one cat. Would it be true that there exists an X such that CX? Yes. Would it be true that there exists a Y such that CY? Yes. So this statement would be true if we stopped here, even if there's only one cat. So what we need to add is there exists an X and there exists a Y, such that both of them are cats and they're not the same thing. Now we have expressed that there are at least 2. So emphasis on at least. What if I want to say there are exactly 2? Well, let's actually pause and say there's exactly 1, because we also know how to express there's at least 1 cat, right? EXCX. How would we say, and if I just said exactly, I meant to say at least, there's at least 1 cat. So let's set this aside. Let's write it down here. So we'll come back and translate this once we do this. So there is at least 1 cat. That's just simply EXCX, because that's what the existential quantifier and sum mean. How would we say there is exactly 1 cat, no more than 1 cat? There is at least 1, but there is no more than 1. Well, the first step is just to spell out what I just said. Instead of writing there is exactly 1 cat, add in that this means there's at least 1, and there isn't more than 1. And here's how we will achieve that. We'll say there exists an X such that X is a cat, and for all Y, if Y is a cat, then Y must be the same thing as X. And we have to have these outer parentheses in order for this X to be in the scope of this quantifier. So this says there's exactly 1. First it says, well, there's at least 1, right? So there exists an X such that CX. That says there's at least 1. And it's the other half that says, and there's not more than 1. For everything else in the domain, if that thing's a cat, well, then it's just X. That's a way of saying nothing else in the domain is a cat that isn't X. As we'll see in another lecture, there are other ways to express this. This is just the way it's usually done. So this says, and there are no more. Okay, so let's use that model then to say there are exactly 2 cats. There exists an X and there exists a Y such that X and Y are cats, and they're not the same, because so far all we've said is there's at least 1 in a redundant way, and they're not the same cat. So far we've expressed there are at least two. This says there are at least two. And for all z, if z is a cat, then what follows? Z must either be x or z must be y. It must be identical to one of those other two because there isn't a third. And then we need to close that, but I didn't leave enough room for parentheses. Okay, and so this is the part that says, and there are no more. Anything else would have to be equal to one of the things, and by equal I mean identical to, as in the same exact thing as one already listed. Okay, so again, you'll see more of this in another lecture video. The point is just that here's a really useful way we can use the identity predicate to say mathy kinds of things, really. We're talking about cats, but we're specifically giving numerical quantities. We're able to say that there are exactly two things, and we could do it for exactly three, but as you can see, that will start to get long. This is already long, and we're only talking about there being exactly two things. Okay, and this is all interesting on its own. What we're going to get now, though, is definite descriptions. So I said before that the present King of France is a definite description. What a definite description will have is, so we've got the two main parts here. We've got the predicate, the thing you want to say about this thing, and then we've got this thing. And the key here, we said this isn't just the name of an object, that's the whole trick. Well, what is it then? We're going to divide this into two bits. We're going to say this is one, an existence claim. There exists a present King of France. And because we're talking about one specific individual, we also have to give what is sometimes called the uniqueness claim. Just to make it clear, we're talking about one unique individual. Not there's at least one present King of France, but there's exactly one. So the uniqueness claim is going to be the same thing we saw before when we said there's exactly one. Here's the existence claim. There's exactly one cat. Well, there's at least one. That's the existence claim. And there are no more. That's the uniqueness claim. Now, unique means exactly one. For what it's worth, things can't be more or less unique, not technically. Unique means one. And so here, I'm not going to call this the uniqueness claim because it doesn't say there's exactly one. It's the and there are no more claim. We could call it different things. But for definite descriptions, we're saying I'm describing an individual, but I'm asserting that it exists and that it's unique in doing it. Again, that the grammar of the actual sentence doesn't make this up. This is like an ingenious way to figure out how to express this sentence such that it has plausible truth conditions, is true or false in a plausible way, and doesn't violate the law of excluded middle. So here's what it'll look like. The present King of France is bald. There exists an X such that X is the present King of France, and for all Y, if Y is a present King of France, then Y just is X. And X is bald. So here's where we've got the simple predicate. This was the part that was never difficult. Here we have the part where we assert that the thing exists in the first place. And here's where we just make it clear. We're talking about a specific individual. Okay, and so all that's left to do is to show how both the present King of France is bald and the present King of France is not bald are both false. Well, by expressing it this way, we have three conjuncts. I'm not going to highlight it because it'll get ugly and it's too much. We have three conjuncts, and we know that a conjunction is true only when each of the parts are true. So each one of these conjuncts has to be true. And because nothing will satisfy this, right? If there is no present King of France, nothing is going to satisfy this. And so both of them are going to be false. And it doesn't matter if this is true or false, negated or not, because this is going to be false no matter what. And it's true that either, let's see, let's pick a new color here. Let's call everything in the parentheses here, let's just call this P. Well, it's true that P or not P. It's true that either there exists an X such that X is the king and the only one, anything else that also satisfies that description is the same thing, and that thing is or isn't bald, whichever thing you say. The negation of that will say it is not the case that there's some X such that X is the king and anything else that satisfies that description is also that same object and that thing is bald. Both of those, in short, the law of excluded middle will be true if we let P equal the whole thing. The first claim is going to be false. And when we stick the negation out front, now it's true. There isn't such an individual who blah, 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 blah. So law of excluded middle saved. It's true that either this or not this has to be true. Okay, as I said before, in the other lecture video, we'll go into a little more depth in talking about numerical quantities, and you'll see a couple more examples of definite descriptions.